Greetings and welcome to the RC Wall Vacuum channel. Today's video is going to be the first in a series I'm going to be doing on electronics and electromechanical projects for RC vehicles. I'm not going to be getting involved with radio setups and ESC programming and stuff like that. Leave it for people who actually know what they're doing with things. No, this one's I'm going to delve more into making devices for setup and maintenance on vehicles, especially the fifth scale vehicles. This particular video, I'm going to delve into the CD underbelly of servo load ratings. This came about because when I was trying to get my Kraken Vecta 5, my calorically challenged Kraken Vecta 5 LSE up and steering, it just doesn't seem to steer that well. You know, I got a 78 kilogram, I think it's AGFRC on there. I figured that would be sufficient, but it struggles with it. So I decided to put together this load tester, and so I can test these servos and see what these ratings even mean into the real world. And then after this one's done and running, I'm going to build an inverse where I'm going to take and set it so you can set your vehicle into whatever train you'll be running on and hook this to the steering mechanism with the servo out and just physically pull on it and see what kind of servo ratings you have to have. And then translate that back to the actual numbers you get on the load tester. So what I'll do is I'm just going to cover the assembly of the tester right now and do some quick tests to make sure it's going to work. And then I'm going to regroup and come up with a series of different tests that I'm going to do on future videos. And so let's go see what this thing's actually going to be made of. So the core frame is made of some square tubing. And the servo carrier is going to be a piece of angle, and I got the this roughly cut out. I got to put it in the mill and square it up. I got to cut slots down through here. And essentially, what happens is the servo gets mounted into here, and it can be adjusted back and forth this way. And the load cell gets mounted up here, hanging off like that. And the reason I wanted to have this adjustable is so that I can put the center axis of the servo. Offset it from the pole point to test lever lengths. So let's head to the welder and we'll weld this up and then we'll go to the mill, do some milling, and then the next stage will be I'll delve into all the electronics and processor stuff involved with that end of it. So there's a cord welded up. I got to go through and determine where I'm going to put that. That's the mount for strain gauge or load cell. So the load cell mounts on there now, and I just got to go over and head off to the mill and make that servo carrier. paint booth, which consists of the great outdoors, step ladder and wire, when it works. This is the servo carrier after it's been machined. I like to be able to identify this stuff from a distance. That's why the bright colors. So I got some rubber feet gonna go on there, and we'll mount the servo, get the slider in there, and I don't yet have the correct bolts for this, but I'm gonna rig it together to work for now. It'll work fine. So there it is assembled. You can see like that right now. I got this, so it's a straight pole on that length arm. Well, like I said, I got this set up down here with slots, so it can be slid way over, and I can put a lot longer arm. And I got some upcoming projects, like a suspension control project, and I have some longer arms. And I want to kind of see what these servos can actually handle load-wise. So the load is sensed here at the load cell. Many load cells, and this one's no exception, consist of a metal fixture that's intentionally and precisely weakened along an axis where you're going to be pulling on. Then 4 strain gauges are placed in an electrically balanced Wheatstone bridge. 2 of the strain gauges are placed on the axis where no deformation should occur, and the other 2 are going to be placed along an axis where you're expecting deformation to occur. When a load's placed on there, one of those strain gauges will be under tension, the other is going to be under compression. Now, the strain gauges themselves are just small little devices consisting of a little flexible substrate, and they got a conductive matrix. I think it's probably like copper. Most conductive substances, anyhow, will see a resistance increase when they're elongated, and it'll decrease when they're compressed. So these gauges get glued to the surface, so the flexing can't occur. The problem is that resistance changes are so small that they're really tough to use on their own. That's why you got to go into the bridge. And I mean, reality is the temperature changes that the gauges will see will cause more of a change than just a strain will. The temperature gets dealt with. I'll deal with that later on, but we won't have to worry about that in this situation. So to make those that small change usable, it's got to go into that Wheatstone bridge. And it's a balanced bridge, and it gets fed with an excitation voltages. In this case, it's going to be 5 volts. So now that small resistance change will actually have somewhat of a voltage change that you can kind of detect. It's going to be very small. I think this load cell is at 2 millivolts per volt, so at a 5 volt excitation voltage, you're looking at 10 millivolts across the whole range from 0 to 100 kilograms. This is a 100 kilogram load cell. So if I was trying to do that with like an 8-bit converter with a 5 volt reference, each bit's 19 millivolts, so you couldn't even see a change. I think a 10 bit's like a 4 millivolts. You see, a couple bits would change, and you could change your reference voltage, put it down a lot lower reference voltage, and that kind of helps it. But what I'm doing here is, and it's a better way of dealing with these things, is I'm going with a 24-bit Sigma Delta A to D converter. I think this one, Avia Semiconductor originally developed this. So now if I'm going with an 8-bit would be 256 points, you're now down to, I think it's 16,770,000 points. So at 5 volts, that gives you a .0000, I think 298 or 0.3 or something like that, or let me start over again. 0.0000, I think it's 298. So we're versus like a 19 millivolts from the 8-bit converter, it would be 0.019. So you can see the difference. It makes a huge factor in reading this. So anyhow, that data gets pulled off of that chip, and then right now I have an Arduino that processes and sends it to a laptop. And so eventually that's going to go onto a PIC, and more on that in a couple seconds. So like I said, I got the Arduino handling the load cell. Now over on the servo itself, I have a separate processor. I think it's a 16F877A, I believe. That's on it right now. Once I combine the load cell and the servo control and the one processor, it'll be probably a PIC 18F452 or a 4552, I think is what I'm looking for. So I don't know if you're familiar with these servos, but to make these things, they're pulse width operated. So to get it to move, you got to send in a pulse width, and it's got to be a certain length. I think it's the general standard is always 1 millisecond goes all the way to one extreme, 2 milliseconds to the other extreme, and 1.5 to the center. The reality is those numbers are a little bit different. That 1.5 will get you to the center, but usually it's like 2.1 or 2.2 full to the right, I think, and then 0.8 or 0.9 to the left. It depends on the manufacturer. And a lot of these servos, you know, even though they run at 7-8 volts, the control signal is generally only kicked out at like 3.3. I think that's what I got to do in here too. I got to feed this one 3.3. Although this is a 5, I think these high-techs are 5-volt tolerant. And since these servos are on battery-operated devices, power savings is an issue. So the moment you send it the pulse width you want, or to get it to the position you want, and then you got to usually wait like 20 milliseconds to give it the next pulse. But if you wait, then this is also manufacturer dependent, like around 50 milliseconds, it'll go into a shutdown mode. So you got to pulse it a certain amount of time. So that's why right now I'm on 2 separate processors, because I want to make sure I got everything working right then, so my timing is right. So I don't want this thing trying to send out a pulse width at the same time as it's trying to grab data off the load cell, and the data comes off the load cell pretty fast. But once I get everything all figured out, the 18F452 will handle, especially clocked around, I think I'll probably be doing that one around 40 megahertz. So that kind of covers some of the electrical details. I'm going to take now and I'm going to get the processors, the 2 processors set up and fed into this thing, and get the laptop over here, and we'll see what we can get out of this for some numbers. So the hookup in this thing, in this prototype stage, is complex enough that I decided to bring it down here into the house where I have my electronics lab. So let me take a quick look at this. So there it is, set up on, tied into the PIC and the Arduino right now. One thing when I was editing the video, I realized I want to clarify some of the numbers I had in there. A 24-bit AD converter will break down to 16,777,777 points, and voltage-wise at 5 volts, you'll get a number that's 0.000000298. That's a pretty small number. So in this current state, in prototype stage, it's obviously a lot of mess to tie in there. When it's all said and done for an integrated design, I will basically just have a box on the side where there will be an LCD like that and a keypad like that, where you just be able to pick what you want to do and control it that way. And everything will be confined, instead of having the 2 different processors, will be in that one processor. So I only have this thing, I just got it set up now, testing it, and that's about as far as I'm going to go for today. But I am going to give a little demo of how it loads up, and I got to come up with a calibration procedure and stuff like that. So in the future videos, I'll start coming up with actual true tests and some real data. So let me just give this thing a quick fire. I got a little loop written in there that will start loading up the servo, and then as soon as you release the switch, it frees it back up, and so you don't strain the servo. So let me get the camera over on the laptop and get some numbers. I'm just going to fire it up real quick. If you watch real close, you can see the servo load up. You can probably hear it buzzing and release it. It goes right back to the center position, and it's back into a fairly neutral position. So unfortunately, I don't have any good screen capture software, but if you watch real close, down at that, right in front of the KG, as I load this up, you'll see that number start to change. So it's definitely putting a load on there. The load cell seems to be scaled pretty well. So for now, I'm just running off a lab power supply at 7.4 volts. I got it throttled back to only a couple amps. Eventually, I'm going to put in a bigger supply that I can give it to 7.4 without a problem, but I'll have its current limited to 10 amps, and that way you don't get full pull on this. And like I said, I got to come up with a calibration procedure on it, and but the whole point was to see if I can get this system initially going. Seems like it's ready to go, and then I'll start getting some servo tests, and over time I'm going to integrate it all into one PIC, and one embedded processor PIC, and then a convenient little package. Another project on the agenda is a 4-point scale, so you can put your vehicle on this scale at all four tires, and then you can read individual weights and then try to balance your vehicle by either adjusting the shock preload or whatever the case may be. This is the first in this series of electronic stuff, so there'll be many more. So if you're interested, stick around. There'll be a lot more coming. I'm hoping the next video I'm going to do is going to be an anodizing though. So thanks for watching.